And in this moment, Professor Yumar Kargin is in Cambridge, is visiting the Cambridge laboratory. And Professor Yumar Kargin, you welcome, and you can start your presentation now. Go ahead.
Okay. Are you hearing me?
Yes, we can hear you. Go ahead.
Hello.
Yes.
Our work. My speech title is Impact. You can see on the slide impact of the thermomagnetic treat on magnetic properties of nanocrystalline iron oxygen and iron cobalt oxygen pressed compacts. Okay. As you know, the magnetic pulse processing here, and after that I will call it MPT technology, is used in mining and processing industries before grinding in mills to soften the ore, or in the process of extracting a useful component. It is generally accepted that in a number of cases, MPT causes magnetostriction and piezostriction effects in grains of ore materials, characterized by the occurrence of deformations. As a result of this, tensile and shear stresses arise throughout the entire volume of ore and the grain boundaries. One of the methods for producing nanocrystalline materials is processing in high-energy ball mills. As a result of processing in such mills, a cellular dislocation structure is formed inside the powder particles, the evolution of which leads to the formation of randomly oriented blocks, separated from each other by high-angle boundaries, like nanocrystalline grains. It is believed that the cheapest materials for making permanent magnets are ferrites. The price level for barium and strontium compounds forces manufacturers of products using such magnets to look for cheaper analogs. An alternative could be nanocrystalline magnets based on iron oxygen. They are cheap, but their magnetic properties are significantly lower than those of hexaferrite-based magnets. So, therefore, our goal was to study the influence of MPT on the formation of the phase composition and magnetic properties of nanocrystalline powder of the iron oxygen systems during their synthesis in a high energy mill and subsequent annealing. You see which kind of materials we used for this work. Basically, all of that. Yes.
Can you hear us? It's in the slide 2. Are you in the slide 2, or are you changing slide?
Sorry.
Because we can see a slide.
Everything is okay?
You are in the slide 2.
Yes, slide 2. Yes,
but we are in the...
Yeah. It's okay. So, on the next slide, you can see the scheme. Sorry, I have some problems. On this slide, you see the scheme for obtaining samples. The processing methods, which consist from some stages, you see in this slide. One of the main stage is the processing when we in high energy mill all our powders. So next slide. So the processing of powder mixture we carried out in this machine by using this machine, which called AGO2U mill. Grinding in this machine has some of the characteristics you can see on this slide. The scheme of the pressing powder in a mold shown in this slide. This on the left side, you see number one, it's our powder. Number two, this is some of the punches, and three is the air buds. Finally, we obtain it like this samples. Each other have the sizes about 10 millimeters in the height, in the length, and the wings. Okay. Next slide. So the installation diagram for thermomagnetic treatment in air shown in this slide. You see this, our samples we put in this center of that installation. Around this, we have change some of the magnetic field by using magnetic flux concentrators. The temperature we measured by using thermocouple, which marked the figure 3. Also, around this, our samples we used, we can change the temperature by using heaters, and we can change the electromagnetic fields by using electromagnetic winding and electromagnetic yoke. So when processed in air in a resistance furnace, the magnetic field strength between the concentrators was about 8,000 kiloampere per meter in a gap of 10 millimeters. To provide MPT in vacuum, we used a vacuum furnace. The processing temperature was 250 degrees centigrade. The magnetic field strength in the system was 4 kilogauss. Based on XRD, data and using the Mersbauer spectroscopy, which show on these two slides, we established that sequence of phase transformation was established. The amorphous phase appears after 16 hours of treatment. The amount of iron melted from the balls is also growing. A model of particles of the materials under study has been proposed. The entire particle has a size about 0.4, 0.5 micrometers, and it consists of Wüsted, alpha iron and nanocrystallites, and some of the amorphous phases. After annealing from the it consists from alpha iron and magnetic powder oxides, which have a size from 10 to 20 nanometers. This is the scheme of how our phase transformation was changing. So the model of powder particles after mechanical activation, after magnetic pulse processing, we can image like this. You see that that particles about 0.5, 0.6 micrometers. So next slide. On this slide shows the dependence of the magnetic properties on annealing time in vacuum of press compacts made from powder of initial composition, 50% alpha iron and 50% hematite. So It is clear from the graphs that the magnetization and residual magnetization reach saturation with increasing annealing, and coercive force pass through the maximum after 6 hours, like shows this. It means that we can say that that alloys heat treatment in vacuum furnace at 250 degrees for 6 hours is optimal. This is blue line is the without field, red line shown with the MPT treatment. On this slide, we can show the dependence of magnetic properties of annealing time for thermomagnetic treatment in air for samples made from powders in composition 2. The content is like this: 50% alpha iron, 30% is hematite, and 20% is cobalt oxide. It's similar, you see. Next. So, also, to find of each phase is responsible for the high magnetic properties, we make some computer modeling. Modeling involves creating an ensemble of particles and specify their magnetic properties. The program calculates the hysteresis loop of the ensemble. The model of magnetization reversal allows one to specify the hysteretic properties of a microvolume of material with several parameters without considering the local values of fundamental constants and structure of a specific defects, since the hysteresis characteristic and consequence of their implementation in the phenomenon of magnetization reversal. We take into account that from a volumetric ensemble consists from 1,000 particles. Since the average crystalline size about 50-20 nanometers, which is close to the critical single domain size for iron and magnetite. It was assumed that all particles were in single domain state. The interaction of particles was not taken into account. The initial parameters of the ensemble was selected so as to ensure agreement between the experimental calculated hysteresis loops. So the ratio of the iron and magnetic phases was taken to be 20 to 80. The magnetization of iron is 1070 Gauss. Magnetic is 480 Gausses. So the selected values of anisotropy fields for iron particles are 3 kiloersted. For magnetic particles, 1.1 kiloersted. It should be noted that these values differ from those calculated using the formula which shows here. Calculated anisotropy fields for iron 7.1 kiloersted, for magnetite 5.7 kiloersted. From this, we can conclude that due to the interaction of iron and magnetite particles, the constant be additively. This is selected values of the anisotropy fields are consequence for the action of certain effective anisotropy constants. As can be seen, the calculated and experimental loops are very close. So next slide. Also, we observe the changes in magnetic properties when the parameter of ensemble were changed. You see here this the amount of iron we change from 5 to 10, 20, 30, and 50%. A change in the phase ratio with the other parameters unchanged affects the properties of the ensemble. you can see the decrease in the number of iron fraction leads to a slight decrease in the coercive force up to 550 Ersted at the fraction of 5% of iron. Increasing the iron fraction leads to monotonous increasing the coercive force. So in this slide, we can generalize all that our dates, obtained dates. You see that the coercive force is monotonically increased from 5 to 50, and the other properties also is increased. So next slide. So we see that increasing the degree of texture increases both the remanence and coercitivity. If we set the micro-orientation angle by a Gaussian distribution with a mean values of 0 to reduce the dispersion to 70, then the coercive force increase to 0.8 kiloersted and the relative remanent magnetization reaches 0.70. So next slide. So in conclusion, it was found that MPT in vacuum makes it possible to increase the value of residual magnetization up to 40%. It is likely that MPT affects the degree of magnetic texture of particles formed during the decomposition of metastable phases. The magnetic properties of press compacts after annealing in vacuum are higher than those of press compacts annealing in air. This fact can be explained by the absence of oxidation of the samples during the annealing process. There are no significant differences in the coercive values of the samples annealed with and without a field. Based on this analysis of hysteresis loops, it is assumed that the particle anisotropy fields in the model correspond to the effective anisotropy constant resulting from the interaction of iron particles with a positive constant and magnetic particles with a negative constant. Based on the comparison of changes of some of the magnetic properties, like coercive force, magnetization of the ensemble at different phase ratios, it is shown that the single domain iron particles are responsible for the highly coercive state of the materials. So, increasing the degree of texture leads to an increase in the relative remanence and coercitivity. I'm finished my speech. Thank you very much. If you have any questions, I would like to answer it. Thank you.
Thank you very much. Claps. Of Professor Zhukov from in Russia and Kazakhstan. Maybe if you have any fast questions, if not, to pass through the other speaker. And well, I have one question about the composition. You said that you are changing, right, or the pressure, how it affects in the magnetic properties.
Yeah. How we change magnetic properties?
Yes, in the hysteresis you.
Okay. As I said, we use first of all we synthesized our alloys by using three different components. First of all, this is magnetic. You see here, yes. Second is pure iron, alpha ferrum, and by adding some amount of the cobalt oxide, ferrum cobalt oxygen. So, and then after synthesizing the materials in this machine, we put in this installation. The main part of this installation is the magnetic electromagnetic windings. You see, this is number 6. This. So,
Okay.
By changing the magnetic fields, we change the magnetic properties of our samples.
Okay, thank you, Professor Yumat. Well, because we are running on time, I can pass to you maybe the email of Professor Yumat Kargin, and you can continue discussing with him much better. Now, thank you.
Happy with this moment. Thank you very much.
Спасибо.
Bye.
Well, but he's happy to give a talk today here. Stuart.
Thank you, Luis. Okay, thank you, everybody. Thank you, Luis, and the organizers for inviting me. It's my pleasure to be here. It's a slightly orthogonal subject. It's not quite magnetism, and it's not quite superconductivity. In fact, if we get the devices wrong, they go superconducting, which we don't want. We want them to be semiconducting. So I'm here today to tell you about the fantastic properties of alpha tin. So alpha tin is it's a different form of tin. It's a semiconducting form of tin. Normally, when we think of tin, the element tin, we think of it as a metallic and superconducting. But if it's grown in a low temperature phase, it's stable in the alpha phase, which is a narrow bandgap semiconductor. So I'm going to tell you about some electrical measurements today. As Louis said, oh, I'm sorry, I'm trying to point to the laser. I'm based at UCL, but I do work with the University of Cambridge, and this work started actually when we had Ximena Velasquez, who joined us. Thank you, Ximena. She joined us with this project, and we started doing this work. We only started doing this work back in February, so it's kind of it's almost like a progress report. It's not really, it's kind of an invited talk, but it's really a progress report of where we've got to in understanding alpha tin. The measurements were done in London, and we did actually rely on materials from our collaborators in the United States. We work with the University of California in Santa Barbara, and they have this fantastic quantum foundry, and there's PhD students involved, and Professor Palmstrong is also involved. So there's my abstract. It's slightly what's the word? Speculative, that's the word I'm looking for. It's slightly speculative. What I've got here in the abstract, you may not have spotted this if this is not your subject, but I've got a Fourier transform here of the bands involved in the transport in tin, and it's rather speculative here, but I'll be explaining what these bands are in tin. The first question that I wanted to answer is, it's a simple question. What is the carrier density in tin? What is it? Well, to determine that, we have to measure it. We have to make a device and measure it. But as I said, we want to avoid beta tin formation. Beta tin, as you know, is a superconductor. It has a TC of 3.7 Kelvin. And it's actually quite useful. It's also quite useful because it's useful as a superconducting contact to a semiconductor nanostructure device where you might be able to stabilize a Majorana fermion. So the state of the art is trying to stabilize a Majorana fermion in these systems and perhaps use this as a qubit device. Okay. So what I want you to take away from this talk today is listed here, the content. I'll give you an introduction, some band structure diagrams of what tin looks like. I'll talk about device fabrication, growth, lithography. As I mentioned, we started with Ximena. She was involved in this work. It's very difficult material to work with because the transition temperature between alpha tin and beta tin is 13 Celsius in the bulk. Now these films are kind of metastable. They're grown by MBE, so they're nice and clean systems. That pushes the transition temperature up to about 60 Celsius. So we have to do all our processing, making the device, blah, 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 up to about 60 Celsius. I'll then talk about the experimental data. We do electrical transport measurements. I'll compare that data with some data from California on ARPES, which is angle-resolved photoemission spectroscopy. You pick up any journal now, Physical Review B or Journal of Applied Physics or any Nature journal, that includes devices on topological insulators, and you will see straight away these kind of false color images of ARPES data. Okay? What we're trying to do is to understand the band structure using transport measurements, okay? In addition to comparing it with ARPES data. And then I'll give you a summary. I'll tell you what I've told you, the ideas that you can take home. We're also sponsored in this work by our national funding agency in the UK, the Science and Engineering Physical Research Council. So I thank them for providing the funding for some of this work. So, introduction, motivation, the band structure. So, I'll just reiterate what I just said, that in the beta phase, tin is a superconductor. Its TC is quite low. It's nothing like the high TC values that we've seen earlier today. It's got a critical field of 4 Tesla, so a nice high critical field. It's got a reasonable critical current, 10 microamps. I think this critical current here is referring to very, very thin MBE grown materials. It may be different from bulk, I'm not too sure. But as I said, it's quite useful as a a superconducting junction between tin and a semiconductor, where you might be able to stabilize a Majorana fermion in the gap, in the superconducting gap. That superconducting gap, energy gap, is about 0.7 MeV. So we need to be really at quite low temperatures for these measurements. So most of these measurements are done in a fridge. This is a paper from the literature. These are our collaborators in California. They grow this material. Here's a TEM image between indium antimonide, the substrate, the semiconducting substrate, and the tin. And you can see here a nice, reasonably nice junction between the two materials. They're lattice matched, they're crystalline, they're high purity. There's no defects here. Part of the problem is the defects in this material, they tend to conduct. So in some materials, the defects give you poor conductivity. With indium antimonide, all those defects, they tend to swamp your device with mobile charge, which is sometimes not good. These are 100 millimeters. So these are possibly SEM images of what the structures look like. So this is an indium antimonide substrate. This is an aluminium. This is aluminium in this case. We've got tin contact here. I think the aluminium is a gate structure. So they're nice, well-defined structures. This is, as I say, this is the beta phase. It's an allotrope of tin. It's a tetragonal phase. The phase that we're interested in studying is in the cubic phase. In the cubic phase, it's semi-metallic. So that's a little bit of background from our collaborators. The actual sorry, is that me doing that? Or is it just, sorry, okay. The actual, no, I'm not touching anything, honest. Okay, that's maybe a loose connection. It's me speaking, I think. Doesn't like me being too close. I'll stand over here. Go back a few years in the literature to see where the band structure of tin was first published, and we go back to 1963. It may be early. I've just picked one paper from the literature that I know. This paper from Bill Paul's group in Harvard. What he did was actually he did a very simple measurement. He applied hydrostatic pressure to a tin device. He applied hydrostatic, or one of his students applied hydrostatic pressure to a tin device. The gap opened up. They did some transport measurements, and they published it in PRL. And it was in the days where, if you looked at PRL, you could have a data plot with 5 data points, and that was enough for your PRL. What they also did was a calculation. They compared it with the crystalline structure of germanium, and kind of extrapolated what tin would look like, that and based on their simple transport measurements under hydrostatic pressure. So we've got this is the top of the valence band here, we've got the conduction and valence band here, we've got other bands deeper into the valence band, we've also got a subsidiary minima at the L point, which is not quite conducting, but may be relevant when you are applying strain or pressure. These bands do move. Okay. We only had to wait for 100 volumes of PRL to appear. That's volumes, not issues. So 100 volumes later to 2013 from 2063. we'd gone from understanding tin as a narrow bandgap semiconductor to a topological insulator, a very, very simple topological insulator. So the band structure is taken from Bill Paul's paper, and there's a calculation from Barfuss, again in PRL, as I say, 100 volumes later. Now, if we look at the band structure here, we've got, it's an inverted band structure. So the states that make up nominally the conduction band are p-like, have a p-symmetry. The p-symmetry is six-fold degenerate here. The electron bands are pushed further down in energy. As I say, it's a diamond structure. When we have this spin-orbit coupling, the spin-orbit coupling effect splits the bands. EF is the chemical potential. That's important because it means that this is where all this behavior is going on in the band structure is something that we can access with a transport measurement and also with an ARPES measurement. With spin-orbit coupling, it pushes down this band, this spin-orbit split band out of the way here. We have a much simpler band here. And with strain, the strain can open up this band gap. And what that does is, with the inverted band structure, it allows this surface state, this topological surface state that I've alluded to in the abstract, to be stable. Okay, to be stable. It's got a small, it's got this small band gap splitting in the bulk, but on the surface, it's got this topological surface state. Okay. It was actually first predicted when topological insulators came along. We had Kane studying this, Liang Fu and Charles, I think it's Charles Kane. They were studying this effect, and they predicted this topological behavior for tin. So it's really thanks to them that this tin is in 2007. It's really thanks to them that this tin has had a resurgence in interest. Just a little bit more data. Sorry to bore you with band structures here. This is nominally what the tin structure looks like. Zero band gap. There's the chemical potential right where the bands overlap. It also means we can get electrons and stable electrons and holes in the system. So from a transport measurement, it's a little bit more interesting to measure and to understand. As I mentioned, the strain was important, and these layers are actually, when we grow these layers, we grow them on indium antimonide. Indium antimonide is the closest lattice-matched surface to grow these materials on. It also presents major problems, which I'll discuss in the talk. But depending on the strain, if the strain is one sense, so it's compressive, if the strain is compressive, it's compressive in 2 dimensions. The lattice has to compress to sit on the substrate. Then we get this topological insulator behavior, a band gap opens up. If it's got a tensile strain, then what happens is the bands shift the other way. The bands shift the other way. So we get this negative band gap structure. And where the bands cross here, we get a kind of the system organizes into kind of a linear dispersion, a little bit like you might see in graphene. So we have a slightly more complicated system. We have these kind of Dirac, semi-metallic Dirac cones with a kind of a linear dispersion to their band structure here. So we can get all this going on in this material depending on how we grow it. We can also add strain to it after we've grown the device. Okay. Let's move on. I'll just skip that because it's a little bit more band structure. Okay. So coming on to onto the practical side of the talk, how we make the devices. As I mentioned, they're grown by MBE, so they're nice. It's a nice clean system, nice interfaces. How we process the devices, and I think since Ximena left us, we'd moved on to making slightly more sophisticated devices using optical lithography, and I'll go through some of that. So, as I mentioned, the wafers are grown in the Quantum Foundry in California. in University of Santa Barbara. They have 7 interconnected MBE chambers. Now, anybody that's worked with MBE knows that that's a staggering number of chambers to have interconnected together. Just having leaks and things not working and problems with cooling and valves sticking, that gives us an enormous problem. But however, we've got experts who work on this. This is I can't even see from there. This is one of the MBE chambers. I think this is their latest chamber. So it's got the usual sources and pumps and peripheral things, but it's also got a low temperature stage so that wafers can be grown at ultra low temperatures, well, low temperatures. So they can do an epitaxial growth at 4 Kelvin using liquid helium. So there's a kind of a liquid helium transfer port in this system. I mean, we do measurements at liquid helium temperatures, but the actual wafers themselves, they're grown at low temperatures and they have to be heated up. They have to be heated up to room temperature to take them out of the system. We looked at several wafers. This is just a quick summary of the wafers that we've looked at. It's not just a one-off. We don't just usually do a one-off. We make several wafers, several devices from several wafers. So they're typically 30 to 50 nanometers thick. We don't need thick layers, especially if you're looking at a topological surface state. It's all on the surface, okay? And the parameters that we're in control of, we can control the growth temperature. Cold might be 4 Kelvin, warm might be 20 Kelvin, okay? The device wafers, they're grown on semiconductor wafers, 2-3-inch wafers. I think you can get 4-inch wafers now of indium antimonide. What we can control is how the surface is terminated, how the indium antimonide surface is terminated before the growth of the alpha tin. So it can be grown, so 001 refers to the indium antimonide crystal direction, centered 4x4 is how the surface reconstructs. And it can be antimony rich or indium rich. So if it's indium rich, it'll be metallic rich, metal rich, antimony rich. And it turns out this is very, very important in determining the electrical properties of alpha tin. It's one of the few parameters that we have control of. So coming on to device fabrication, we started off by making these. This is a chip package that we would use to cool the chip down to low temperatures. It's only about 1 centimeter across or smaller. The problem is we can't heat it up. So we have to put down silver paint contacts. We kind of wire bond across here, put down silver paint contacts. But you can't anneal the contacts to a high degree, otherwise it changes over to beta tin, to a superconducting phase. So this is to carry out a simple Van der Pau method. I don't know if people still use Van der Pau methods, but it's a really useful method for determining the transport properties of an arbitrary shaped device. If you've got a bit of time today, look up Van der Pau's paper. It's really a classic paper, 1958. He worked at Philips in Eindhoven, and he kind of put together the simple mathematical proof needed to do this type of measurement. So that's the kind of measurement that we do. And the more sophisticated measurements that we'd moved on to was to make a hall bar. We can etch. It turns out it's quite difficult to etch tin. You would think you put a bit of acid in there, it would just etch away the tin. But this metastable form of tin seems to be quite resistive to acid. But anyway, we can kind of eventually make these hall bars, so we can apply voltage, we can apply currents. We can probe different areas of the device. We can also put things like nanostructures in here on the top. This is about 80 microns across, so it's a nice well-defined current path. This is just an optical image of the device. So these are kind of evaporated aluminium contacts. The fact that they're superconducting is immaterial, but this is what the device looks like. So that's the processing. Coming on to experimental data, I'll tell you a little. Oh, I'm sorry, I pressed the wrong button. Tell you a little bit more about the results of the transport measurements. I'll compare that with the ARPES measurements. I'll then tell you about what happens at low temperatures and the application of high magnetic fields. So the Van der Pauw transport summary, as I said, look up Van der Pauw's paper, it's really quite interesting. The problem for us is, once we put contacts down on devices, this very, very thick substrate. Now it's very difficult to get insulating indium antimonide. It used to be quite easy to get, because you could get p-type doped indium antimonide. If it was p-type doped, you cool it down, it's extrinsic, you'd lose all the holes. But it looks like the electronics industry that perhaps uses indium antimonide has no longer use for this material, so we're stuck with undoped indium antimonide. The good thing about undoped indium antimonide is that you can apply a magnetic field. When you apply a magnetic field, you get a nice metal insulator transition in the indium antimonide, and it freezes out. So typical values, low temperatures, 1.5 Kelvin, typical field range, 3.5 Tesla. And we have to kind of permute where the currents and voltages are measured on the device to get out resistivity and Hall effect. From the Hall effect, we can get the Hall constant and then eventually the carrier concentration. And I'll just remind you about the question that we were trying to answer at the start of the talk. What's the carrier density in alpha tin? Okay. This is what the substrate looks like. So this is rho XX as a function of field. This is kind of the different permutations of contacts that would make up rho XX. If you average them out, it kind of goes parabolic. So you think, well, that's probably going very insulating. If you look at the Hall effect is asymmetric in field. So by doing a subtraction between positive and negative field, we can get out the Hall effect. I plotted the Hall effect, excuse me, on a log scale here, so you can see it's linear at low fields, and then really at higher fields, we lose carriers, which is really how we can measure these devices. Okay. The first data from tin, this is rho XX, this is wafer 1, this is the indium terminated substrate, and we know there are, after measuring the devices, there are big differences. It seems like how the chemical potential is pinned at the substrate interface really determines what you get. The substrate is dominant, so this is the tin in parallel with the substrate. It's not very interesting. It's freezing out. There's no Hall effect. I think this is still the Hall effect from the substrate that's freezing out. So really there's not much to report on this particular wafer. Okay, I'll just move on to the next one. On the next one, again it's indium terminated. We've actually got in rho XX this time, it's gone negative, which indicates a kind of a hole density. So that was quite, when we saw that, that was quite good because it indicated that we probably had got some semi-metallic behavior going on in the system. We got some N-type behavior and P-type behavior. Okay, but still nothing, no magneto oscillations or any quantum Hall effect that might be going on. This is a slightly thicker device. Rho XX starts to show this unusual behavior. Rho XY again shows this. It's starting positive and then goes over to being negative. So whether that's really a crossover induced with field, I'm not sure. We're trying to model this with N and P carriers. You have to kind of make assumptions about their mobilities. Okay, so that's kind of ongoing. But we're starting to see now that the substrate is less dominant. Moving on to the antimony terminated substrates, they're starting to show much more interesting behavior because, well, this is rho XX, not so interesting. In rho XY, we're starting to see oscillations in rho XY. We're not seeing a quantum Hall effect. This resistance is far too far below h over e squared to be quantum Hall effect. So it's not quantum Hall effect. We can get the mobility if we know the Hall constant and the resistivity, we can get the mobility. The problem is this resistivity is a resistivity at zero field, and the current really shunts the indium antimonide shunts the current, so we can't get those values. But what we can get is we can get the mobility from where the magneto-oscillations start in field. Okay. That's the third wafer. The magneto-oscillations are a little bit clearer. Oh, I'm sorry. Magneto-oscillations are a little bit clearer here. This is still only at low fields. I'll show more data in a few minutes where we push this up to higher fields. So what we've got here is we've got the indium antimonide substrate, we've got the substrate freezing out, we've then got some magneto-oscillations in the material. As I say, we can see magneto-oscillations in rho XX, but it's also quite interesting that we see the magneto-oscillations in rho XY. So there's an effective medium going on in there. This is just a summary of these wafers. We've got the substrate termination. As I say, there's a difference between indium and antimony terminations. The Shubnikov-de Haas effect is really not visible in the indium terminated surfaces. I think because the Fermi energy is pinned too low or too further down in the gap to have any carriers that would produce this Shubnikov-de Haas effect. Rho XY, we can get a sign change, so we've got electrons and holes in the system. We've got a variation of resistivities. I mean, you can see here 10 to the 5 resistivity for the indium terminated surface. So we've got N and P type behavior. We really need an effective medium theory to understand this. And we've also got these magneto-oscillations in rho XX and rho XY. Okay. So I'll move on to the higher field measurements. When we apply a high field, we've got access to several magnet systems. Our standard 1.5K system has an 8 Tesla system. So this is the data up to 8 Tesla. I've drawn this, so this is RXX. You can see the oscillations developing. There are two sweeps here, sweep up and down. This is kind of an expanded view. So I've taken away a linear term here. If you take away a linear term on the background, you haven't adjusted the oscillations, you just made the oscillations clearer. This was the first data where we could really get out the question, what is the mobility in the system? So we know when we start to see a magneto-oscillation, we know that mu b equals 1. We get a charge going round a cyclotron orbit, so we know that the angle there is 1. So that gives us a mobility of 4,000. Okay, not too bad, 4,000 centimeters squared per volt second. Now, if you were to look at beta tin, it wouldn't be anywhere near that value. So we know we've got alpha tin here. Okay. Now we've got these Shubnikov-de Haas oscillations. As I'm sure most of you know, they're a harmonic series of oscillations. They're periodic in 1/b. You can characterize their minima here with an integer, Landau level index, integer n. Okay. And they form a nice series, n times bn, where n is the Landau level index, bn is the field, where we get the magneto-oscillation minimum. You plot those out. If you plot n as a function of 1/b, the gradient here is the fundamental field, and it nicely goes through 0. So it's a well-behaved electronic system. If we calculate the carrier density from this, if it's a 2D, we still don't know if it's 2D or 3D. Shubnikov-de Haas effect from this fundamental field gives us 1.4 10 to the 12 per square centimeter. That's a huge density. These are undoped films. That's a huge density. But it could be that it's 3D. It could be that it's 3D. So if you work out what the carrier density is, if these oscillations were 3D, it's about 8.8 10 to the 17. Now that for a semiconductor is quite a high doping level. Okay. These are antimony terminated surfaces. This is wafer 4. So it's slightly different. This is rho XX as a function of field up to 8 Tesla. Again, reasonably well-defined data, low noise. If we expand the scale again, so I just take a linear function, I'll take a linear function off this data and plot the data out, you can see here it's not just a single series of oscillations. It's I can't give an n value to any of these minima here. What I've done on this graph is I've plotted the derivative, first derivative of rho xx with respect to field. You can see, first of all, this is just the substrate. This sudden increase here is just the substrate. But on top of that, we've got this magneto-oscillation where there's a whole series of oscillations going on, which is great. That's exactly what we wanted to see. We wanted to see something from the surface, something from the bulk, and possibly, depending on the strain in the system, whether we have a Dirac semi-metal. We could Fourier transform this. That would pick out the number of frequencies in the system. We can also compare with angle resolved photoemission. We can also compare with lower temperatures. It might be that at lower temperatures that these oscillations are better defined. It also might mean that the metal insulator transition in the substrate, in indium antimonide, is better defined. Okay, and obviously higher fields would be useful for these measurements. So this is the ARPES data. This is not my data. This is data from California. And they have a system there called the Advanced Light Source, which is, I think, in Berkeley, California. I think it's a synchrotron source. Please correct me if anybody knows differently. But they can do these angle resolved photoemission measurements. And typically how the system works is you fire a high energy photon. So this is the photon that's fired at the surface. It's done in a vacuum. Electrons are emitted. You can measure the energy of the electron. And from the angle of the beam, you can determine the in-plane K momentum that you're imparting to the electron. So you can kind of work out what the dispersion is doing in the system. It's slightly awkward because each energy and momentum measurement has a resolution, and you kind of get a convolution of the two. So each data point here is a kind of a convolution of the two measurements. So the outer are the heavy hole states, and then this is at 53 eV. There's a hint of another state here. At 21 eV, incident photons, it's slightly more complicated and possibly a little bit more interesting. We have the heavy hole states out here. We have a state here, which we've labeled this topological surface state. So we've got two clear states and a state that we don't quite know. We think that's possibly another surface state. Question is, which of these states are involved in the transport? Do we have L valley conduction? As I showed you in the second or third slide, we have the L minimum, which can be populated and perhaps contribute to the conduction. Or do we have an additional heavy hole state in the system? So just coming towards the end, we've got measurements at lower temperatures and higher fields. So it's the same type of measurements. This is rho XX. This is the antimony terminated substrate. Basically, we haven't measured the indium and terminated substrates because they don't really show very much at lower temperatures. This is rho XX as a function of magnetic field now. We do several sweeps just to make sure we know what we're measuring. I've expanded the plot again. So this is rho XX minus a linear term up to 10 Tesla. You can see, this is quite a useful study actually because you can see several things. You can see this, these minima now, they've shifted actually. They've shifted by a half. So you can't assign an integer to the minimum now. You have to assign a half integer, or an integer minus a half. What's also interesting is if you look carefully here, you can kind of see a beating. So it's not just one frequency, it's a beating of frequencies. So it's quite good that we've got two frequencies here. Okay. you could see that before we did a Fourier transform. Obviously, a Fourier transform confirms that. I'll just go back to these minima again now. So if we plot the minima index minus a half as a function of 1 over b now, it deviates from that. It starts to deviate from that. But this half, this factor of a half here, tells you straight away that we've got this extra phase in this system, which is very, very characteristic of a topological insulator. So the carriers now in a magnetic field take on this Bury phase, so-called Bury phase. And because of this number is a half here, that Bury phase is pi. So to understand this data, at higher fields, that's down, at lower fields you don't really see, which is this end of the scale, you don't really see that. It's only when you go to higher fields that you start to see this deviation. Fundamental field, we knew that anyway because we'd done measurements at 1.5 Kelvin. What we also get is, from measuring the carrier density, we can also get the Fermi wave vector. And that Fermi wave vector that I've estimated here agrees very well with the ARPES measurements. So that's kind of a self-consistent. If you Fourier transform this data, so we Fourier transform this data, this is Fourier amplitude as a function of fundamental field. The oscillations are periodic in 1 over b. That means they are characterized in the Fourier transform by a characteristic fundamental field. And what we see here is this fundamental peak here split. Now I think that's quite important. That splitting, it's that splitting there that gives rise to this beating effect. Okay, so we see beating. There's evidence of multiple frequencies, and we've got this topological phase. We've already identified that topological phase, and it's kind of developing. It's developing at high fields. What we also see here is this noise. Now you might say, well, you know, that Stuart Holmes fella, he doesn't know how to do measurements. It's all noise here. He's just measuring noise. But it turns out this data down here, it's not noise. And I'll show that, I think, in the next slide. No, I'll show that in the next slide. This is Hall effect data. We also, so this is a Hall voltage now that we're measuring, plus minus 10 Tesla, the Hall effect. What we see is a mixing of rho XX and rho XY, but if we kind of demix them, this is still a van der Pau measurement, by the way. This is still a van der Pau measurement. It works up to high fields. We see these very, very clear oscillations. We've got the same fundamental field. We still don't know what the carrier density is. We've got no carrier density from the Hall effect. We've got no quantum Hall effect. But what is interesting is these magneto-oscillations are a lot clearer in the Hall effect. We still don't quite understand that. Okay. So, as I mentioned, that we've got this Fourier transform of the magneto-oscillations. When we looked in rho XY, so the previous slide, we see very, very clear extra frequencies coming out in the system. So we've got these extra we've got the 3 frequencies, but we also know from this rho XX measurement that this frequency here has this Bury phase of pi. If we just got the 3 frequencies, we wouldn't be able to tell which minimum was which. So it's been very, very useful to do this study. So we've got 3 bands of carriers. We've got A, B, C, so that's A, B, C, A, B, C. There's evidence of peak splitting. This is a little bit of noise down here. So there is kind of evidence of peak splitting. This peak doesn't split. This peak doesn't split, which may be coming from a heavy Hall state. It's not, you might say, well, it's just spin. But if it was a spin splitting, you'd get a peak at twice the fundamental field. So this is more likely to be a spin orbit type spin splitting. But as I say, we managed to pick up this Bury phase of pi, which is coming from a topologically protected surface. What we saw in the fourth sample, so again this is rho XX as a function of field. I've expanded the scale here, so it's this scale taken minus a linear term up to 10 Tesla. This is where we see very, very clear 3 frequencies. This is plotted as, well, first of all, I was trying to identify which minima here corresponds to which fundamental field. It's very, very different. It's very, very different. This is actually now rho xx on an expanded scale in terms of 1 over b. So sometimes if you plot out the data as a function of 1 over b, it's very, very clear which minima corresponds to which frequency, but not in this case. But again, this 4th wafer was very, very clear in giving us these 3 frequencies. I think this is the last of the data that I'll show you. This is Hall again. This is Hall voltages plus minus 10 Tesla. Because of the van der Pau, we do get mixing between RXX and RXY. We can take that out. This shows amazingly clear oscillations. I mean, there's a bit of people have nibbled at this in the literature, but this is very, very clear data. Very, very clear data. If we expand out the plot, we see multiple frequencies here, very, very low noise measurements. And it did occur to me when I was doing this measurement, it's very good actually because the characteristic impedance of the device is 50 ohms. Most electronics, your lock-in amplifier, your preamplifier, they all want to see a characteristic impedance of 50 ohms. This material has that characteristic impedance, so we were very, very lucky with this material. Very, very clear Fourier transform. This is the bulk. This is the state. This is a topological surface state that we know has this Bury phase of pi. This state here, we're not sure what it is, but it's very, very clearly split. Okay. What we can also do is we can measure the mobility from this Fourier transform. So it turns out you can measure the so-called single particle mobility. It's not the classical mobility, the zero field classical mobility, but it's single particle mobility. If you go through the algebra of this Fourier transform, the quantum mobility is √3 divided by the half width at half height. So the half width at half height is that blue rectangle there. It's about 2 Tesla, I think, in fundamental field. That gives us a quantum mobility of 9,000. That's great. So we've got the 3 frequencies, we've got the high quantum mobility. We still don't know what the carrier density is, unfortunately. Okay, so just to summarize, I've nearly finished. How long have I got? 1 minute. Okay, so I've only got 1 minute left. This is a summary of these measurements. This is what I want you to take home, okay? We've got 3 bands of carriers in this material system. There's a big difference between antimony terminated and indium terminated. We see those 3 states in the ARPES measurements. It's unlikely to be the L valley. It could be the bulk tin hole state that's coming in. So we kind of agree with this band structure here. We definitely see this topological surface state because we know it has a Bury phase of pi. Future developments, gallium ion beam patterning. I've already done that. I was about to show you that data, but Lewis has said I can't show you the data. I'll have to come back and show you the data. We want to move on to tin germanium alloys. I'm also applying to do measurements at 30 Tesla. In France, or in Europe in general, we have a network of high field labs. You can apply for funding there. So I'll be going to Grenoble to do measurements at 30 Tesla. I'd like to do a direct hole measurement, okay? I've also put in for funding on this. We made a quantum wire. The problem with the quantum wire, it's not quite a quantum wire, it's almost a quantum wire. It looks like a quantum wire. Electrically, it doesn't behave as a quantum wire. The problem is when we fire gallium, when we try and pattern using a gallium ion beam, we tend to create beta tin. So part of the device goes superconducting, which is not ideal. That's some transport measurements. I think this is my last slide. So this is magneto resistance as a function of field. This is a series of quantum wires. Doesn't really show very much, I'm afraid, but we'll get there. Beta tin formation during the processing. We can pattern beta tin. We've got this topological surface state now, and we definitely know it has this Bury phase of pi. We were very, very lucky with these measurements. The obvious question to develop, the obvious question is, can you develop the dielectric and the gate metal combinations so that you can move the chemical potential between those bands and really identify what's going on. I still haven't answered the question, what is the carrier density of alpha tin? Thank you. So, thank you.
Thank you very much. Thank you very much, Professor Stuart Holmes from the University College London and University Cambridge. Well, if anybody has a question, raise your hands. Yeah, a question there.
My question is, how do you control the termination of the indium compound substrate?
In the MBE chamber, the wafer is annealed. Before the growth of the tin inside the MBE chamber, the wafer is annealed at higher temperatures. And I think if you anneal it you get the indium termination of the surface just by heating it to higher temperatures. I think if you anneal it in an antimony environment, you get the antimony terminated surface. Then you cool the wafer down and grow the tin. So it's a standard technique. I don't know the details, but it's a standard vacuum technique for terminating the surface. The surface reconstructs, so it forms its own symmetry on the surface. And using an X-ray or using electron diffraction, you can determine which one it is. Yeah.
I have another question. Is the indium compound very fragile? Is it broken easily? And how do you manage to do the UV lithography, photolithography?
So it's done at, they're not particularly fragile. Once you've drawn the tin on the indium antimonide, it's fairly stable. It's fairly stable. It's not as stable as silicon, but it's fairly stable. It's not brittle. It's not brittle. So they can be handled with tweezers and wafer handling tweezers. What we do for the lithography is we set a thermal budget of 60 degrees. Nothing goes above 60 degrees. So you spin on photoresist, you vacuum anneal it, or anneal it at 60 degrees. It goes into an etch at room temperature to define the structure, and then you put metals down using a technique of lift-off, and the lift-off never goes above 60 degrees. It seems to work. It shouldn't do, but it does work.
Can you please explain me what is the physical significance of the fundamental field and the fundamental frequency?
Yeah, so the magneto-oscillations have an oscillation periodic in 1/b. So you get them all at high fields, but the 1/b, the low field information is important. So if you Fourier transform that, you have to consider that it's periodic in 1/b. Okay, so the Fourier space of something that's, if your variable is x and your space is 1/x, the Fourier space is x, has dimension x. So it's just the dimension of the frequency in this case. So it's a number that characterizes the oscillations that are periodic in 1/b. If you've never done this type of measurement before, it takes a while to understand that. So apologies for my rather coarse answer there.
Just one last question about the topological insulators. How can I understand it better?
Sorry, I missed the first part of your question.
Sorry?
Could you repeat the question, please?
No, because I wanted an explanation about the fundamental field, but now what about the topological insulator?
So with the identification of the topological insulator has come from, first of all, a prediction, and number two, the fact that it has this Bury phase. So if you plot out usually in the Shubnikov-Tahas effect, your minima in the oscillation corresponds to an integer harmonic. If you have a Bury phase, or if you have an additional phase that's coming in, it gives you a phase shift to that. and the integers are no longer minima in RxX. Okay. Usually nature is quite kind to you. It gives you pi. So the Berry phase gives you a pi phase shift. So that's why the half comes in. It's half of 2 pi, which is just pi. Sorry.
What about the Van Halfen effect?
Yeah.
Also, you can just finish, please.
So yes, you would. So that is an oscillation of the magnetization. You could probably dope the material with some probably manganese or even iron, and it would show an effect if you haven't damaged the mobility. But the Shubnikov-Tahas effect is much easier to study in a kind of in a diamagnetic system.
Yeah, but what about, what do you think? The technique is almost the same, or?
Yeah, it's the same equipment you would use. It's the same equipment.
It's just oscillation, right?
It's the same. It's the same process. Yeah, it's the same. It's investigating Landau level structure in your band structure. Yeah, it's using a field to split up your density of states into Landau levels. So it's the same principle. Yeah, it's just a different measurement.
Thank you for your interesting talk. The question is, when you have multiple charge carriers,
yeah,
it might be useful to vary the direction of the magnetic field,
yes,
to see how it affects the quantum oscillation.
Yeah.
So can you comment on it?
Yeah, so thank you. That's a good question to ask. So we have what we think is some two-dimensional behavior. So if you rotate the device in the magnetic field, it will respond to the perpendicular field component if it's two-dimensional. The problem is, in the three-dimensional films, if you calculate, they're only thin, if you calculate the elastic mean free path, it's greater than the sample thickness. So you will get some so-called quasi-2D behavior when you rotate the sample round. So that's the problem. But I totally agree, that's what I want to do in Grenoble next. Yeah, thank you, that's useful.
Mauro.
What are the thermal properties of these such systems? Do they have a high, say, thermal conductivity or not?
We haven't really looked at that. That's a good question. I know that a related material, bismuth is also roughly a narrow bandgap semiconductor, and that has a very high thermal conductivity. So several years ago, I tried to make some bismuth nanowires to take away heat from a chip device. Whether tin has that, I'm not sure. I'm not sure of the literature on the tin, but if it was found that tin had a high thermal conductivity, then that would be in agreement with bismuth. I have to say I'm not sure. Yeah. But it wouldn't surprise me if it has a high thermal conductivity. Yeah.
Okay, I think that is no more time for more questions. Now you are invited to go to have lunch. You have a break, and we recommend 3 places. If you want to go to the Plaza San Miguel, you can need to take a taxi on the corner, or a bus maybe. Plaza San Miguel, or also you can eat around here at the university. If you prefer a very, very economical, there are more students who knows that where to move inside the university or around there. And also you can ask for some direction to Professor Ángel Bustamante or to Dr. Juan Carlos González as well. We see us again here at 2 p.m. Okay? Thank you. Free Wi-Fi is there on the wall, the code. On the wall there is a code for